Hello, I'm Shihan from Korea University. Today I'm here to present point cloud augmentation with weighted local transformation. Due to data acquisition challenges for 3D vision, only limited data are available for training deep models. Data augmentation is one approach for remedying this issue, yet it has been less explored. Existing conventional data augmentation in point cloud is from PointNet, which consists of global transformations. Recent works like PointAugment, trying to learn an augmentation network, and PointMixup, interpolating two point cloud samples, have emerged. However, these works are all fundamentally limited to global augmentation. Here, we propose local augmentation for point cloud data. Here is an original wolf, and given an anchor point, we can naively apply the local transformation in a range of a local ball like this, T1, T2, and T3. As all we can notice, samples are unrealistic and disconnected. In contrast, based on the distance from an input point to the anchor points, our PointWOLF differentially applies the local transformation using the Gaussian kernel. So by weighted summing local transformations, T1, T2, and T3, the final smooth deformation is able to generate realistic samples to improve the generalization power of the deep models. Next, we concentrated on how to control the strength of augmentation. Here is an original human class sample. Augmented samples are generated from a range of augmentation strengths, weak to strong. If the augmentation goes too strong, the sample gets broken, which can interrupt the model training. We suggest AugTune, an effective scheme to adjust the strength of data augmentation with a single hyperparameter lambda called a difficulty coefficient. As a result of AugTune, we want to generate the final augmented P star with a target difficulty, which has a reasonable scale between the difficulty of the original P and the augmented P prime. Given a lambda from range 0 to 1, we can compute a target confidence score C as shown in here. To generate P star with the target C, AugTune uses linear interpolation between P and the P prime with alpha star, which is the solution to the following equation. However, due to computational costs, we approximate alpha star by alpha tilde with this equation. We expect the final CP star to be close to the target confidence C. Our experience shows this approximation does not cause the performance degradation. In sum, the final input for the model from AugTune becomes a linear interpolation of P and P prime with alpha tilde. With PointWOLF, we achieve consistent improvements in overall accuracy on both synthetic and real-world dataset. Especially, we observed PointWOLF significantly improves the performance with real-world data. For instance, on perturbed scan object NN with PointNet++, the performance gains are about 3 to 6% compared to every baseline. These are some examples from PointWOLF. For example, compared to the original airplane, the first augmented airplane has a bigger tail with raised wings, and the second one has a shorter head with the wings down. In addition, we analyzed the robustness to various corruptions. We observed PointWOLF help models to learn robust features against local and global corruptions compared to CDA. In summary, we propose 3D data augmentation produces smoothly varying non-rigid deformations by locally weighted transformations. Our diverse and realistic augmented samples bring consistent improvements over existing augmentations. Third, we validate the importance of understanding the local structure and improve the robustness against various corruptions. And lastly, we suggest an efficient scheme to adaptively adjust the strength of augmentation during training with a single hyperparameter. Codes are available at our GitHub page. Thank you.